Good morning, children. My topic for today is imperfections in solids, taken from your chapter Solids. Ideal crystal is an ionic crystal which has the same unit cell containing the same lattice points throughout the whole of the crystal is known as ideal crystals. All the atoms are present in their respective places. Now, ideal crystal can be seen at 0 Kelvin, absolute zero temperature only. As the temperature rises, some of the ions, they get enough energy to move from their respective sides, move away from the respective sides, thereby causing a defect. A defect is any deviation from completely ordered arrangement of constituent particles in a crystal. Now, broadly speaking, defects can be of two types: point defects and line defects. Now, the defects which arise due to irregularity or deviation from ideal arrangement of atoms around a point or an atom in a crystalline substance are called point defects, whereas the defects which arise due to irregularity or deviation from ideal arrangement in entire row of lattice points are called line defects. Now, point defects may be caused by either a vacancy or because of presence of interstitial defect. So in vacancy defects, point defects can be because of two reasons. In a vacancy defect, some of the lattice points have left their place and these points are vacant. There are no atoms in these places. Then interstitial defects arise when some atom occupies a vacant interstitial site. The crystal is then said to have an interstitial defect. Here some cation is occupying an interstitial site. Now, vacancy defects and interstitial defects, these arise in non-ionic solids only. In case of ionic solids, the defects can be classified differently. So, in case of non-ionic solids, the defects in crystals will be stoichiometric defects, non-stoichiometric defects, and impurity defects. Now, stoichiometric defects can be classified into Frenkel defect and Schottky defect. Schottky defect is a type of a vacancy defect where equal number of cations and anions are missing from their regular sites. The place which is devoid of a cation will be called cation vacancy, and the other site where the anion is missing will be called anion vacancy. Now, the compound which has the equal number of cations as well as anions and they conform to their normal chemical formula are called stoichiometric compounds, and the defects in these compounds are called stoichiometric defects. Despite the defects, the number of cations and anions remain the same. So in Schottky defect, which was given by the German scientist Schottky in 1930, it says that cations and anions are missing from their regular sites. The conditions when such defects arise are those compounds which are having high coordination number, they show this defect, and where the cations and anions are of similar sizes. In case of Frenkel defect, a cation leaves its normal space and occupies an interstitial site. So, This kind of a defect is similar to an interstitial defect in non-ionic solids. This is an interstitial defect in ionic solid. It is called Frenkel defect. Now, those compounds which have low coordination number and where the anions are much larger in size than the cations, they show Frenkel defect. So these were the defects in stoichiometric compounds. These were the defects which are called stoichiometric defects, Frenkel defect and Schottky defect. We may also differentiate between the two defects. Schottky defect arises when equal number of cations and anions are missing from their sites. These arise when cation leaves its regular site and occupies an interstitial site. The density decreases because of missing of cations and anions, whereas here the density has does not change. And this type of defect is shown by compound showing high coordination number. This type of defect is shown by compound showing low coordination number. Examples of Schottky defect are sodium chloride, potassium chloride, cesium bromide and silver bromide. And Frenkel defect, silver chloride, silver bromide, silver iodide and zinc sulfide. So because in these compounds the cation is small enough to leave its regular space and occupy the interstitial site. You will also see that this compound silver bromide can show both Schottky defect and Frenkel defect. Next is defect in non-stoichiometric solids. These defects are called non-stoichiometric defects. Now these are of two types: metal excess defects and metal deficient defects, metal deficiency defects. Now, non-stoichiometric compounds, those compounds in which the ratio of positive and negative ions present in the compounds differs from that required by ideal chemical formula of the compound, are called non-stoichiometric compounds, and the defects in these compounds are called non-stoichiometric defects. So in metal excess defect may occur due to two reasons. One is because of an anion vacancy and other one is because of presence of an extra cation in interstitial site. So in case of anion vacancy, an anion is missing from its regular site and an electron occupies its space in order to keep the crystal overall electrically neutral. This occurs when alkali metal halide crystals are heated in atmosphere of alkali metal vapors. For example, when crystals of sodium chloride are heated in an atmosphere of sodium vapor, the excess of sodium atoms are deposited on the surface of the crystal. The chloride ions will diffuse to the surface of the crystal and combine with the sodium atoms to form sodium chloride. As a result, the sodium atoms will get ionized and sodium chloride will be formed. The electron that the sodium atom loses, it will diffuse back into the crystal and occupy this vacant anion site. These electrons, these are responsible in imparting color to the compound. So these electrons trapped in anion vacancies, they are called F centers. F in German means Farbenzenter. For example, the presence of electron in sodium chloride imparts yellow color to sodium chloride crystal. Similarly, violet color to potassium chloride crystal and pink color to lithium chloride crystal. Another type of metal excess defect, another reason for metal excess defect may be due to presence of extra cation in interstitial site. For example, when zinc, in case of a zinc oxide crystal, when zinc is heated, when zinc oxide is heated, then it loses its oxide ions loses electrons to form oxygen gas, and oxygen gas diffuses out, leaving behind zinc ions. Now these zinc ions are small enough to occupy the interstitial sites. So they move into the interstitial site, and because of which this metal excess defect is caused. Zinc ions will be more, oxygen will be less. And in any of the adjacent neighboring sites, electrons will also be trapped to keep the crystal electrically neutral. So this is also a kind of metal excess defect. So zinc oxide is showing metal excess defect, where this is an interstitial kind of defect where extra zinc ion is present in the interstitial site. Another kind of non-stoichiometric defect can be metal deficient defect. So this defect may again arise due to two reasons: either because a cation leaves its regular site and causes a cation vacancy, so this is metal deficient defect due to cation vacancy, or an extra anion may occupy the interstitial site and may cause metal deficient defect. Now metal excess defect when arises in crystals, these crystals may, their conductivity is increased and they may behave like N-type semiconductors, because the electricity conduction of electricity is because of normal movement of electrons, whereas metal deficient crystals, these behave like P-type semiconductors. Their conductivity is also increased, but their conductivity is because of increase in conductivity is because of movement of holes, like a hole is created here and a cation from neighboring site may leave its place and occupy this hole. As a result, another hole is created here. So here the movement is because of positively charged holes. So this kind of conductivity is called P-type semiconductors. These kind of conductors are called P-type of semiconductors. So metal excess defect compounds show N-type of semiconductor behavior, and metal deficient defect compounds show P-type of semiconductor behavior. You may also observe an interesting phenomena here in P-type of semiconductors. For example, in case of iron sulfides or iron oxides, you will see less iron than oxygen. Iron content is about 93 to 96%, whereas oxygen is 100%. This happens because out of, say, in case of iron sulfide or iron oxide, 3 ferrous ions, instead of 3 ferrous ions, 2 ferrous ions will change into ferric ions, and third site, which was occupied by ferrous ion, is left vacant. So instead of 3 ferrous ions, there are 2 ferric ions and 1 site is vacant. So this is responsible, in case of ferrous sulfide in iron pyrites, this is responsible for a gold-like metallic luster to the compound. So iron pyrites are also called fool's gold, because it's not real gold, it just appears like gold, so it's called fool's gold. So in metal deficient behavior, defect behavior, you see this interesting phenomena. Third type of defects are impurity defects. In this case, when, say, a crystal of sodium chloride is doped with an impurity of strontium chloride, then a divalent 2 sodium ions will be missing from their regular sites, and a divalent strontium ion will occupy the place of one of the sodium ion, whereas the other sodium ion remains vacant. So this again results in increase in conductivity. This has occurred because of introduction of an impurity to the crystal. this kind of defect is called impurity defect. You may also later on study that if the impurity, if an electron rich impurity is added to a metal, then the conductors which are formed, semiconductors which are formed, are called N-type semiconductors. And if an addition of electron deficient impurity is given to the crystal, then a P-type of semiconductor is formed.